Hi, I'm Dave McKinnon. I'm the General Conference Chair for the 2021 Electrical Insulation Conference. The EIC organizing team welcomes you to the 39th conference, which is fully sponsored by the IEEE Dielectrics and Insulation Society. Our organizing team has planned an exciting conference for you. This year, we have 170 papers. We have 15 live question and answer sessions in all time zones worldwide for both oral and poster presentations. We have 2 open discussion sessions for all participants and sponsors. We have 2 days of live dissection workshop. We have 3 short courses. We have 2 student meetups, and then we have 2 student expert panels where students are able to interact with experts from all over the world. I want to thank our organizing team for the great job on this year's conference. I especially want to thank Nancy Frost for all of her contributions and support. Thank you very much. I also want to thank our technical program chairs, Alan Stravacci and Anna Gaganova, for all the hard work they've done putting the technical program together. Thank you very much. I also want to thank Mark Winkler for all the hard work you've done putting the publications together. Thank you very much. I want to thank our reviewers for the many hours you have spent peer reviewing papers. Thank you very much. We really appreciate all the hard work you do in peer reviewing papers. We also want to thank the session chairs for helping out with all the Q&A sessions. Thank you. I want to also thank all of our participants for this year's conference. You are what makes this conference so successful. We really appreciate your attendance and participation in this year's conference. Thank you very much. I want to thank our sponsors for their contributions to this year's conference. I especially want to thank our platinum sponsor, Von Roll. We have a short video to watch. Thank you.
Welcome. Von Roll is proud to be the platinum sponsor of IEEE's 2021 Electrical Insulation Conference. We hope you enjoy the virtual trade show. Thank you for joining us today.
Von Roll has been producing high-tech insulation materials for rotating machinery for over 100 years.
Welcome to our labs. I'm Christoph Herold, and I'd like to take you on a short tour through our labs.
Here, at the laboratories, Von Roll tests the performance of different insulation materials. Mechanical and physical properties are tested in our material testing laboratory. This also includes testing the behavior of materials under high thermal, electrical, and mechanical stress. Special challenges in practice arise from so-called partial discharges. These discharges damage insulation and weaken the efficiency of a machine. In a worst case, they can lead to total breakdown. Von Roll's Corona Protection System successfully prevents harmful partial discharges. The Von Roll Institute's eDrive laboratory performs various high-frequency tests. Partial discharge diagnostics makes these effects visible and analyzable.
Welcome to Von Roll USA in Schenectady, New York, where we combine on one campus the complete product portfolio of Von Roll. This is the home of the leading and most recognized product portfolio in the industry, like our mica tapes called Mica Matte, and our flexible laminates known under the brand AccuFlex, as well as our wide product portfolio for coated products like Thermal H, FusaFab, FusaFlex, Fabritherm, and Corona Shield. Our testing labs for high voltage as well as our application lab are an integral part of our DNA. On our campus, we produce and test our industry-leading brands for resins and varnishes, Dolphs and Permafill, which include our full line of impregnation resins, trickle resins, encapsulation resins, varnishes, and potting compounds such as Dolphin, Synthite, Hightherm, Aquatherm, E-Solder, and E-Coat. Whatever your needs, training, testing, field service support, experienced technicians, or custom formulations, Von Roll is here for you. We are proud to be your single source for all of your insulating materials.
I also want to thank our gold sponsors for their contributions to this year's conference. Our gold sponsors are Electrolock, Hypatronics, and Atlantis. Thank you very much. Lastly, I want to thank our silver sponsors for their contributions to this year's conference, Delft University of Technology and TEPCO Power Grid. Thank you very much for your contributions. The Electrical Insulation Conference provides an international forum to share practical experience, research, and new technologies in all areas of insulation. The Electrical Insulation Conference provides an international forum to share practical experience, research, and new technologies in all areas and applications of electrical insulation. This year has brought many challenges throughout the world and brought forth how critical reliability is in all industries such as power, paper, and food, and many others. The Electrical Insulation Conference is founded on electrical insulation, which is one of the major components in systems and system reliability. When selecting a speaker for this year's conference, we wanted someone whose passion and drive is to improve reliability. One person's name came to mind, that of Alan Ross, who is this year's speaker. Alan is a certified reliability leader, a certified maintenance reliability professional. He is also a member of IEEE Reliability and Power Energy Societies. He is chair of the Smart Grid Reliability Alliance. Alan completed his undergraduate work in mechanical engineering at the Georgia Institute of Technology and his MBA in marketing from Georgia State University, graduating magna cum laude. Although great achievements, these do not show the many great things Alan has done to improve reliability in industry. Alan is well known in industry, often presenting at conferences, writing books, writing articles, and even working with government. The title of one of his books, Beyond World Class, is a great description for his efforts and for this year's presentation, Effect of Reliability Principles on Insulation Lifecycle Management. In this exciting presentation, Alan will discuss the opportunity the Electrical Insulation Conference has in the role of industrial reliability.
Thank you, especially for those of you who join from around the world. I know it's hard. I had to do 2 presentations last week, or discussion recordings last week, and they were with New Zealand, and it was, I had to stay up until 10 o'clock and do this live, and it was hard. I do better in the morning. Anyway, I appreciate what you all are doing, and I want to talk through, I want to take a different approach. We talk a lot about technology, and in many of our conferences, as you said, Dave, you got I think it was 170 or whatever, it was a tremendous number of presentations that people are providing, and we get down into it. What I realize as I go around is that we have a platform in the reliability world that I think will make every IEEE in the power energy society, at least, and in the reliability society, I think it will have a tremendous impact if we understand things from a reliability perspective. So that's what I really want to do. I'm going to take a journey through how I think, and that should scare you. The fact that I'm going to let you into my mind ought to terrify you. But I want you to see how I think as I think about reliability. So we're going to walk through this, and there you go. So most of us on here, we know this, but we say this I'm the editor-in-chief of Transformer Technology magazine, and we have a lot of papers and presentations and articles that we put in there. And one of the things that I appreciate is how many people, if they're talking about transformers, or even folks in the EPRA world who are talking about cables or breakers or anything, we all come to this conclusion that the life of the insulation determines the life of the asset. Assets don't wear out. Electrical assets don't wear out because the copper doesn't work. They don't wear out. I mean, sometimes they get taken out because you'll have a lightning strike, but they don't wear out because the metal doesn't work, because the electrons don't move. They wear out because the insulation deteriorates, or it was installed incorrectly. So the life of the asset, and that's something I think we ought to really push. The life of the asset is the life of the insulation. So what does it mean to you guys as EIC professionals when we talk about this? It means that you're at the actual forefront of life cycle management. When you talk about life of the asset, that's the life of the life cycle management. Unfortunately, things like transformers have lasted for 38 years. The average power transformer in the United States is 38 years old. They were never designed to operate for 38 years. They were over-designed to operate 20, which means that we have relied on this extra life. The asset has been written off on the balance sheet, so nobody really pays attention to it until recently, because now we're starting to see aging failures, or failures that because of the weakness or because of the condition of the asset, they fail whenever we have some form of an event, like a lightning strike. And interestingly enough, we don't hear enough about it, but lightning storms are more prevalent today than ever. So when we have hurricanes, when we have tornadoes, when we have all kinds of problems, we have lightning strikes, which are taking out electrical equipment. Weak insulation will then make the asset weaker. So it may last for another 10 years. However, it is not going to last. It's like an old man with a heart problem. He may sit down in his armchair and last another 10 years. But if a burglar comes in and he's got to run upstairs to get away from him, he may die on the stairs. So it is that external event that happens that we've got to be taking into consideration. So how does the reliability of insulation impact the reliability of the asset? What are the ways it does it? Let's approach it from reliability challenges. I am basically on a mission to implement reliability principles in the electrical system. There are organizations, SMRP, the Society of Maintenance and Reliability Professionals, who has certified me as a certified maintenance and reliability professional. Reliability Web, Reliable Plant, the Noria Group. There are just a Marcon down in Tennessee. There are a number of reliability organizations out there. You know what they all have in common? None of them have anything about electrical system reliability. They're all on the mechanical side of the world. In the utility business, there are resiliency principles, there are redundancy principles, but there's just until recently, there's not been a lot of reliability principles brought into even in the utility world, particularly in the grid edge. And we'll talk about that more. But as you see these problems, if you can approach them from an electric power reliability mindset, of which I'm going to talk about, you're going to be able to, I guess what it is, raise the bar in terms of electrical installation. So if you're going to raise the bar, there ought to be thousands of people on this conference, because you should be talking about the very thing that most of everybody else in the reliability and maintenance world is talking about, life cycle management. So let's approach it from that. As I said, we have an aging infrastructure. It is older than it was intended to be. When I was at Georgia Tech, I used a slide rule. I don't know if most of anybody on here would probably know what that is. Most people, because it's an antique. I can't find my old large in the leather case slide rule when I used to, run from one class to the other in Atlanta at Georgia Tech. That thing would flap against my side to the point that I got a bruise on my right side of my thigh because my slide rule was smacking it. That's how we design things, and we overbuilt them. And we overbuilt them for a reason. It didn't cost that much to put a little bit more copper in, a little bit more insulation in. And people specified a product like a transformer, breaker, cable systems, and we overbuilt. Based on the specifications, we built tanks. And if you think about it, it's like cars built in the 1950s that are still driving around in Cuba versus the 60s and the 70s, when the car industry in the United States became more about how many poor cars could you make. And we lost our leadership in the auto manufacturing because we no longer overbuilt vehicles. The ones in Cuba, by the way, are still operating. We've also got this generational transfer of knowledge. That is a reliability principle as much as it's anything, because so many of the old guard, I can talk about that in my age group, they knew the legacy knowledge of how to keep things running. They knew the weak points because they've been managing them for a long period of time. But as they retire, if we have not captured it, then guess what? The next generation doesn't know about those weak points. The other thing is the next generation may not need to know about them. Why? Because maybe some of the stuff that we knew is no longer valid. So the idea that the next generation is learning and growing and they look at information differently is also a reliability challenge. Oops, sorry. I don't know why that's working that way. Digitalization. I just walked into a room that I had not been in for 14 months and met a group of people, and 4 of the 5 people that I met that I did not know all had something about digital in their title. And I thought, that's if you want a job today, just put digital in your title. So I am now the president of digitalization of the Electric Power Reliability Alliance, because everything is changing, and it's changing much more rapidly. COVID didn't change it, but what COVID did was move things 10 years forward, I think. In our industry, the big issue right now is monitoring and diagnostics. They're putting monitors on everything. One of the problems is it's really hard to monitor the insulation in a system because it's inside of a system. So what they do is monitor the entire system. That doesn't necessarily mean it makes it more reliable, by the way. I keep doing that, and I got to stop doing that, Rachel. So how do I do that? Click there and do this. I have a producer. Power quality and automation. I'm going to leave it alone because we got a lot to talk about on that. And then insulation is part of an asset. The asset is part of a system. Ergo, insulation is a critical part of a system. And that's one of the things that in many reliability aspects, we focus on the asset and we do analysis and over-analysis, and we don't look at the impact of that asset on a system. So I would challenge you to think about the impact of insulation on a system, not on an asset. And that whole mindset leads us to the point of the weakest asset in the system shows the weak link in the system. But shouldn't that also be the weakest insulation, the oldest, the cheapest sometimes? Hey, yeah, let's do it. You don't have to put all that dollar into it. What we've got to do is get to the point where people understand the specifications of the insulation for the reliability of that asset. So I got to say it again. The specifications of the insulation is one of, if not the most critical component of the design and specifications of an asset. And you all are doing some amazing things. I know I was on we did a Power Pro thing here recently, PowerPoint sharing with some folks from Weidman. And we were talking about specifications specifically for transformers and a project that they had worked on with Delta Star, who makes mobile subs, who have to be, they have to be smaller to get in streets, and especially in New York City. And this was a sub for New York City. And they went to the highest level of Nomex product for all of the cellulose in there. They put on the highest heat treated paper. Why? Is because they wanted to make the smallest, best, most reliable transformer that they could move around whenever the Hurricane Sandy came in. And so consequently, they were talking about, which was last week, they were talking about specification of the insulation for that transformer. It is critically important, and we need to raise the bar on that. So we did a focus group. We do this every year. I'll publish the 2020 pretty soon. We're a little bit behind on it. But we asked senior corporate reliability people, do you have an electrical system reliability program? You can see that. 50% of them are in deer in the headlights. What does that mean? Which we would say is no program. There were some of them that said, yeah, we probably know we should. That means 75% of the corporate people did not have a reliability program. Now, we're very specific in that, because by that we mean it's not your maintenance program. We'll talk about that in a minute. It's a reliability program. And if they did, they would design their new assets differently, because all reliability begins at design. All design begins at specifications. All specifications build at the point of what its functionality, what is the function of this asset supposed to be. And what we've done is we used to, as engineers, we had a lot of say in it. But now in the world of, hey, you're not allowed to let any engineers talk to the bidders, it's become a bidding war. And so consequently, we, and when I say we, I'm in it too with you, those of us in the insulation world, we know what the best insulation is to put in it. But when we're in a bidding war, what happens is we put the cheapest. It may be very good, but it's the cheapest, not the best. It's not necessarily the most reliable. It's just the cheapest. We've got to get out of this purchasing mindset and get into a mindset of, through insulation, you can bring about a different outcome in that asset. And for example, the one about the mobile sub that Delta Star made for New York City, the most important part of that was we built it based on specifications for size, for heat transfer, because what we needed was something that could withstand running at overrating or running at rating consistently. So there were a lot of things that we got to work on, that Weidman got to work on when we did the specifications of that. Now, when you look at regular, from whether it's a GSU or whether that's just a distribution transformer, we can have the same impact. We can overbuild today. But what we got to do when we overbuild is we've got to make sure that we overbuild correctly. So, when you look at these things, and what are you trying to avoid, is in the world that we live in, and I apologize for this, but we all are under this maintenance management mindset. You know what maintenance is? I was the CEO of a company decades ago, and we had 400 employees working in 7 different plants. And I never had anybody come in and say, we'd like to spend more money on maintenance. All of the plant managers looked at maintenance as a cost center. What we're supposed to do is just keep the machines running as cheaply as we possibly can. And guess who was the hero? This person we call Maintenance Mike. He's the guy that goes in and, hey, that machine was down for only 7 hours because Maintenance Mike is the hero. He can go and fix it. And there's some guy called Lucky Larry who's in the back office there. And Lucky Larry has kept his machines from ever failing. He's not the hero. Maintenance Mike is. We also have this maintenance, MTBF is mean time between failures. MTTR is the mean time to repair. These are two big maintenance and reliability acronyms, but they don't fit the electrical system. The mean time between failure of transformers, as I said, is 38 years. It's probably longer than that, but we just know that power transformers are 38 years. When your mean time between failure is 38 years, you're not thinking in terms of maintenance or reliability. You've completely lost it. And mean time to repair, well, that depends. It depends on what it operates, and it depends on the system. You know, the mean time to repair cables is a heck of a lot longer than any maintenance or plant manager realizes. Because in many instances, you know what you got to do? You got to break up concrete, you got to dig up cables, and you got to put it in. We had one case where the plant was in an area and they had sold off land that what their primary feed to their substation went under, and they never got an easement. So this was a cable system that ran under part of the new plant that was built a decade after they had done this one. It was not on the one-line diagram. You know why? Because it came from the utility into the main feed. But it was their main feed. If that line had gone out and it had been spliced 7 times, not in any of the diagrams. And so consequently, the failure that would have come from these transformers was because of the failure of the cables. And to try to get that dug up, you had to get the other company to basically allow you to tunnel under their building or to take a quarter of their building. It wasn't going to happen. We ended up having to bring cranes in, large cranes that could be kept off of the other person's property to replace 4 primary transformers at great expense, just because they couldn't take the potential of a hit. And then in the maintenance world, it's all about spares. You don't have spares in the electrical world, spare cables. We might have some breakers and we might have some relays, but for the most part, we don't live by spares in this MRO, which is the maintenance room, all of the spares that you got in there. Oh, I got 7 spare motors. How many spare miles of cable do you have? None. How many spare transformers do you have? None. How many spare breakers do you have, especially SF6 or other gas breakers? None. And so you can't live in that world. So what is the world we live in? You know, this could be much more complex, but I really want to focus on the left-hand side. I don't care whether it's transformers, breakers, relays, protect, no matter what you do, if it's in the electrical system. This is true of even the mechanical side, but this is the way we think in the reliability world. All reliability begins at design. Ergo, all unreliability begins at design. And design begins at function. And function begins at specifications. And you begin to look at it and you say, you can see why the products that we're making are not worse today. They don't last as long. They are not as reliable, not because they're not good components, but because we don't begin at design. We're just giving a specification for a rating of something, and then we make it to that rating, not realizing that we should probably consider the fact that we run electrical systems powering the system in Houston, Texas at 120 to 130% of rating through the summer. Why? Because it's hot and humid and every air conditioner in the city is running full bore. Can you imagine what's going to happen when 7 million people plug 7 million cars into a grid to get charges on those grid? I mean, it's going to be a nightmare because we're designing for unreliability, not reliability. In the electrical insulation world, you ought to be screaming about design for reliability. And that means you need to put things in that will take over ratings, that can take the kind of abuse we subject these electrical systems to and can be built. And the cost of it should not be about the cost of the asset. It should be about the total cost of ownership. That's a huge thing in the reliability world. We're not there. We've been pushing it for a long time. A gentleman named Ramesh Gulati, who is one of he's on Mount Rushmore of reliability. And Ramesh Gulati and Ron Moore and several other great people all agree that reliability begins at design. But Ramesh has brought in the idea with statistics, with analysis, why total cost of ownership is so important. And he is not an electrical system guy, but he does talk about insulation in his book, because he talks about designing for something that can withstand the kinds of treatments we're putting electrical systems through. And then operations, maintainability. Is it easy to maintain, hard to maintain? And ultimately flipping back over life cycle analysis. How long was it designed to last? The entire electrical system, grid and everything, has not been designed to last as many years as it has. So you know what that means? Is waiting for something to happen. And when you have weather events like we do, or fires, or now you have all the cybersecurity issues that we do, when you look at it, you're saying we're not necessarily designed as it should be on that chart up there for reliability. We should look at the functionality of it. What is the impact on the system if something goes out? Oh, if that cable goes out, this whole system goes down. If that transformer goes out, the system goes down. If the breaker doesn't work, the entire system goes kaput. But we start to look at things that from a reliability perspective, we're not just looking at the operation of the asset, we're looking at the operation of the asset within that system of assets. And what we're trying to do is maximize the life and utilization. You know, in asset management, they're competing with us because for the most part, a lot of asset managers are looking for the lowest cost, lowest maintenance cost, lowest purchasing cost. They are not looking for the total cost of ownership. And from technical engineering, I don't think they even consider total cost of ownership, because they're down into the weeds. What does that asset do? What does it look like? How do I make it cheaper? There are not many of them that are saying, how do I make it more reliable? So when you look at a high voltage system, these are the significant issues that each of the different assets are going through. All of them are obviously going through aging, but the poor maintenance of transformers, the oil is dirty, it's got water in it, and water is more moisture that you've got in a transformer, the quicker you're destroying the insulation. So the moisture and insulation life are kind of inversely related. The higher the moisture, the lower the life. And what we found is in over 100,000, one of our organizations tests 100,000 transformers a year, oil sample tests. And of those 100,000 transformers every year, 64% of them have excess IEEE standard excess moisture, 64%. And it's killing the insulation. Now, are there insulation products that you can make that would help wick away moisture? Probably. Are there insulation products that would help? Well, I know there is oil product insulation. You can actually use FR3 or some of the plant-based fluids, and they actually wick away some of the moisture. So there are things that we can possibly do, but you know, for transformers, aging and poor maintenance, it's happening. Cables and buses, aging and splicing. As I said, we did one organization and the cable had been spliced 7 times and never recorded. So anybody who you know is anything about cable will tell you the weakest link of the cable tends to be at the connections or at the splices, which is also where the insulation becomes important. But when I go back to transformers for a minute, I was talking with a gentleman who came up with an epoxy that is the new way. Instead of using ceramic around a bushing, they use an epoxy now that fills in. It's much, much better. It's actually self-cleaning, and it has a huge positive insulation factor, but it's not cheap. It's not as cheap as just putting porcelain on there. And so consequently, they've got to get into the design phase, what you need to do in order to design it correctly. Breakers, I can't tell you how many times we say, do you test your breakers as you're supposed to, manufacturer's recommendation? And most people don't have any record of that. We also have new gas breakers. SF6 came along, and now the EPA would like us to do away with that. And IEEE and others are working on a new standard for gases with a new gas that is not something that EPA is concerned about. And then, of course, relays, batteries, all of these new things we're putting into the system impact power quality, and they are battery life regulated. But this bottom one is the one big issue for power quality that we'll talk about. Moving along, this is the biggest change. We live in an electromechanical world, and we're putting in solid state things daily. Robotics into automotive plants. What do they have right next to each robot? They have a small dry type solid state transformer. And the reason that they have that power quality is critical. And so in this world where we're changing out using microtechnology, even nanotechnology, it does have an impact on the electromechanical system, because the electromechanical system is forgiving. In the solid state technology, it's not as forgiving. So we better be more careful about what we specify in terms of insulation. You know that this is the, we could talk about one-line diagrams. I have, in electrical things, if I'm talking to E&I people or plant people, and I say, how many of you have an accurate one-line diagram? I was talking to an internationally known hospital group, 17 facilities, some around the world, in London, Dubai, or excuse me, Abu Dhabi, and Florida, and in the Cleveland area, an unnamed internationally known hospital. I asked the question of 17 different E&I guys, electrical and instrumentation guys who are responsible for electrical systems. How many of you have an accurate one-line diagram? About 2/3 of them raised their hand. That's scary. It's a hospital, for gosh sakes. The others didn't know and didn't know where it was. Like, maybe I ought to go back to my office and find it, or they're brand new, or whatever it was. Okay, how many of you have added new assets into the system? Every one of them raised their hand. How many of you have redone your one-line diagram in the last 2 years? About 1/3 of them. The rule of thumb is if you add assets to a system, you've got to redo your one-line diagram. You've got to do an arc flash study every 2 years. It is woefully inadequate in terms of what's being done in the electrical system is too dependent on what you all have done in insulation in the past. And if we're not careful, the purchasing people are going to push us to push insulation to the lowest possible denominator, as opposed to the highest reliable denominator. Let's start using that word, highest reliable denominator for our specifications. We did something across the top are a bunch of assets. There's, I think, a total of 27 assets that are in an electrical system. And down the left-hand side are all of the testing standards, IEEE, NFPA, all of the things that you ought to be doing. We very seldom find anyone following those standards, by the way. They're operating the system as if the system is going to last forever, and it's not. This is my version of the one-line diagram. It's a step-down system. Our entire electrical system is built generation to the transmission, to the distribution, to the industry, or to the house. Everybody's happy, all step down. This is the world we're going into, step everywhere. In order to be a smart grid, we've got to take into account that we're going to have distributed energy resources, power and wind and other. And it's going to come in and it's going to now compete with coal and hydro and gas. It's not just competing for price. It's competing for EPA and cleanliness and the whole new green technology. Can you imagine what's going to happen when we electrify transportation? The entire grid is going to change. The amount of charging capacity needed at light surpasses anything that we're doing today in generation. So not only do we need to change out and we're trying to replace these coal-powered plants, but now what you got is you're going to have competing needs, and the demand for energy is going to change. Vermont Electric, Velco, has a lot of wind and solar that they run on, but they have to have the old system ready to go when the wind don't blow and the sun don't shine. They've got to have gas generation ready to go online, so they have to keep it ready to go. Because you know what? That's their job as a utility. This is changing everything, and I think it's changing it for the better. So we've got to look at the role insulation plays in this. So our body of knowledge, I'm going to go through this quickly. We look at all of these things: criticality, analysis starts it. That's where you look at functionality and you say, what is the critical function of that asset in this system? So today, criticality analysis is primarily based on an asset view. What we're trying to do is change it in the reliability world to be a systems view. We also need to change it to say, don't look at the asset, look at the insulation to start with, because that tends to be the weakest point. And all of these things are the words that we live by in reliability. But here's what's changing. We're adding this: artificial intelligence and machine learning. Everybody's adding it. And it augments what we're doing as humans. The problem with this is too often we're taking historical data and doing a simple extrapolation. That's machine learning. You're taking this historical data, you're letting the machine continue to learn, and then you're saying, hey, if you extrapolate that, it goes here. Artificial intelligence, we hear a lot about it in the electrical system world. I have honestly not seen one good example. I've seen a lot of examples where they're talking about machine learning, but I've not seen one good example where artificial intelligence has really helped us. I wonder if there's going to be any that we can use in the electrical world. I hope, Dave, that you've got a couple of presentations that are going to be looking at AI and how it can be used, because we just haven't seen it yet. Somebody needs to step up and say, here's how it really, really works. Here's the, I have a thing up there, I call it the UIoT. IoT, everybody knows, the Internet of Things, right? There are 27 different monitors you can put on a transformer. A utility in the southeast of Ohio, southeast of the US, put these on it. They said, these are the ones that we wanted to do. By the way, 7 different data sets. They had to go to 7 different places. So even though they could monitor, they went all over the place. So here's my deal is, what is the useful Internet of Things? Let's start using the UIoT. Because you can monitor it, doesn't mean you should. And where does the data go? It better go somewhere that you can use it. I was asked to write an article for Efficient Plant magazine on power quality. So I had to become an expert. And I approached it from reliability. And I looked at it and I thought, I got to give them something that I can talk about from a case standpoint. Schneider Electric is probably the best known in terms of going into facilities and doing power quality analysis. And I'm not going to talk about the issues of power quality, the harmonics, the sags, the spikes, and all of the other things that happen. But I want you to remember that harmonics line here, the one that's buzzing up and down there. And this is an interesting thing. EPRI did a study in 2001. Now get that, 2001. And they said, who's going to be affected most by power quality? They said there are going to be 3 parts of the economy: the continuous process manufacturing, that's huge in the United States; fabrication and essential services, huge in the United States. And these are the ways that they're going to be affected in the billions of dollars. I wonder if they were to update that, what that would look like today. These are not millions, these are billions. Power quality, these are aggregate losses because of outages in these regions in the billions because of power quality issues. They give as references some great references: IEEE 2005, IEEE 2014, IEC, and it's also referred to in IEEE in 2017. And so there are probably 1,000 more that we could probably give here. And that's what we need to be doing. We need to be giving standards and references that show the damage done by unreliability. My last little thing here, I love this one. There's a dairy plant, or dairy processing plant. They make products that they have to flash freeze. They have old refrigeration units that they have to manually pull the trays out from the bottom and move them to the top in order to be able to keep the temperature correct in there. So the refrigeration people came in and they said, we got new ones. You never have to do it. The fans will automatically change temperature to keep every tray the same. There'll be one control unit. You won't need all of these human beings and you can't make any mistakes. Life is going to be good. Buy them all. And they did. They spent millions of dollars. They installed them and they began to fail. And they failed randomly. It was like this one failed, and then that group failed, and then this one. So they're going crazy. Now they have not put the plant back up and running, but they're now days away from now using this new system. Oh, by the way, what did they do with the old refrigeration units? That was a question I asked, nobody knew. But the whole point was they were no longer there and had all these new units. So they brought the folks from the company that made them, and they brought all the engineering and the contracting folks. They're all working on this thing, big problem. And of course, the company, CEO is involved now, saying, you need to take them out. I want the other ones in. They promised us this would work. Everything was going to be great. And there was an electrician, a second shift electrician. He saw all these suits, as he called them, guys with ties and suits. And he said, what are they doing over there? He asked one of the controllers, and they said, oh, we're having all these problems and everything. He said, well, have you looked at that main feed from the transformer? Because it's always had harmonics in it, but it never affected anything. They install a $1,500 controller transformer, and it removes the harmonics, and the machines don't shut down. That's the whole point about when you bring about change into a solid state system or this new micro technology from one controller, it's happening over and over again. And harmonics that didn't do anything before now does things. So when you look at the minor things that we can fix when we talk about specifications of insulation, it's a big deal. People ought to spend the money to do what they need to do. The last thing, Google Brains. Oh my gosh, I used to be the smartest person in the world with my children. They asked me a question like, why is the sky blue? And I would say, well, when God made the sky, he decided that he wanted us to have eyes that just loved it, and the green. Well, that's not true. But now my kids go, Dad, that's not true. I Googled it. And so I'm no longer the smartest guy in the world. But the next generation from millennials down are Google Brains. They can find data and stuff. It's not that they need more data. They need more data-centric decision-making, and they need to be taught how to critically think and do that. And unfortunately, we're not doing it well enough. I hope we're doing it well enough in the insulation world. On the left-hand side, that was data that literally 12 years ago, we used to take all of this data and turn it into a kind of a pie chart. Look at what we do today with that data. If I took this to a CEO, the first thing he'd do is he'd say, okay, what does the red mean? Or in this case, orange. What are the outliers? What's the problem? What's the issue here? He never looks at the green areas of the things that are working. It's what's the broken part here. So when we look at digitalization of the system and reliability, we've got to give people data that they can use in a way that helps them make accurate decision making. So the same is true when you ask people to upgrade or to work on or to specify or to invent or to do anything with electrical systems. I know I've gone a little bit over, but I get excited when I talk about this area, and I think the folks on this conference should too, because I'm in the world of reliability, and I can promise you, we depend upon the work that you do in order to create reliable assets, in order to create reliable systems. And there's no better place to start than at this conference. And with that, I will open for any questions if anybody has any, but Dave, you need to control the time, I know. And Dave, you're muted.
Does anyone have any questions?
I can't imagine no one is asking why the sky is blue. Nancy, go ahead, ask me why the sky is blue.
I wasn't going to ask why the sky is blue. I'm going to actually dig into, or ask you a little bit more about that. 64% of the transformers have excessive moisture. You knocked my socks off that data.
And unacceptable moisture, 64%.
That's, yeah. Now, is that part of the, do you think that's part of the fact that we're using transformers that were designed for 20 years and are operating at 38 years, or is it new designs, or just kind of that number? I'm astonished that we're having our assets having that kind of red flag, shall we say, or yellow flag. It's not a red flag, but it's a yellow flag, and things are still working. I'm waiting for that catastrophic failure. So what are your thoughts on that?
That's exactly your point. That is a weak transformer waiting for some form of anomaly to happen, and it's going to fail. If it were not a wet transformer, it could probably withstand that anomaly. But how does moisture get into transformers? Because companies have these online systems now, these things that are called dry maxes and moisture max and all that,
Yeah.
and they attach them to the system, right? And so they over time take out the moisture. Here's the problem with that: if you have a leak, you're just continuing to take out moisture. So the first thing any of these people should say, they don't all say it, is, you know, fix the leaks. You know where most leaks are? Leak number one comes in the gasketing.
Yep.
You think about it. A transformer 38 years old. It's sitting on, you know, it's got bushings coming into the top, bushings coming out of the side. Gasket material gets weak and it gets hot. The sun shines and the moisture comes down and it cracks. And suddenly you get ingress of moisture in. The radiators, you've got this very thick steel and a very thin radiator material that is hand welded, okay, to that 38-year-old transformer. And one bead, it was fine for years, but as a little bit of rust starts, all of a sudden you have a problem. If you go into any substation and you look at transformers, go to where the radiators are and look and see if you see fuzzing. Fuzzing is where right around a radiator seal, there will be a little bit of like, it looks like dust that catches, and you rub your hand on it, you'll note that there's probably something like oil there. That's a leak. Moisture's getting in if stuff can get out. So consequently, the two weakest links are those weakest links. So we scream about that. Fix those and then dry out the moisture. There is natural tendency of cellulose to give off moisture once it's put into a transformer and operated.
Right.
That too can create moisture in the transformer in a sealed system that, guess what? If you don't get it out, it's going to be there. And the last thing you want it to do, if you've used poor insulation, I liken this as, don't have somebody go buy some pine tree wood chips from Georgia and make it into an insulation block and put that into your transformer. It's cheap, but I can promise you that piece of block has got more moisture in it than it's got anything else. And we see it over and over again. I think it's primarily the aging of the transformers means that you have much more aging of bushing material. The bushings may not be failing, but that for certain the gasket material is failing.
Thank you for that. Appreciate it.
Yes, hi, this is Claudio. I have a question for you. You make reference to the bidding war going on for when you have new assets. And this is really one of the biggest issue we have, because it's all a question of how long you want your asset to last. And then for those who are buying it, it's always what's the cheapest you can get it from. So have you, in your experience, tried to come up with some figures of the total asset value for the company compared to what they save as they purchase the asset?
The best work that's been done on that cloud is by Ramesh Gulati, who's absolutely the author of Total Cost of Ownership. And Ramesh, we will get a link to his book. It's available through reliabilityweb.com. They're the publishers of his book. But Ramesh is, and I think he just came out with a new edition, and he put more on that calculation, how when you're calculating total cost of ownership. Another gentleman is Ron Moore, M-O-O-R-E, and he's done some statistical analysis on total cost of ownership. But it is a relatively, it's an old phenomenon that we're now just addressing. And one of the things that I have tried to make people aware of is, if you're always dealing with the purchasing person, it doesn't matter what statistics you give them or numbers. You have to get procurement involved. Procurement looks at the total cost of the asset, the total cost of ownership. And I think that's part of it. In the bidding wars, you've got to break the specification barrier. You know, we're not allowed to talk to engineers. You're not allowed to give information. And you know what it is. You could say, oh, by the way, if you just did this, you'd save this much and long term. And the purchasing guy will block you. If you were talking to me as an engineer, I go, oh, done deal. I'm going to put that in the specs. But I think there's a pendulum. Engineers, we used to control specifications because they didn't have this push. Now you got this pendulum the other way. purchasing controls it. We can't even be involved in it. We don't even get involved in the discussion. So the deal is we've got to get the engineers in the utility world, in the reliability world, to get to us first before they say, I need a new asset, and to talk to us about what they think that asset should do, how long it should last. Make sure that they ask for some form of total cost of ownership versus cheapest cost as a calculation into it. So I think in the meantime, and most people, Ramesh is really well known in the reliability and maintenance world, not so much in the electrical, but he's someone that if we can get the reliability engineering involved, they will understand this, and they can then help get procurement involved. And then I think we will change the mindset. The pendulum has to come back, maybe right in the middle. Maybe it's not all engineers rule everything and we get whatever we want, right? But we overbuilt the world back in my Georgia Tech days. Now it's like we can't even get what we know will last 10 years. It scares me for what the electrical system is going to undergo in the next 10 to 20 years, that we're building it as the lowest cost. It scares me to think what's going to happen 10 years from now.
Yeah, well, thank you very much. I'll have a look at those because we definitely need to bring the pendulum back.
Okay. Yes, Claude. Either that was very, very good, or many of you are asleep, or some of you are actually going to bed. I know that, but we had one gentleman from Japan that was, it was 10 o'clock when he started this thing. So it's time for his bed right now. Dave, I'll turn it over to you.
Well, I had one question, is going a little bit farther back in the development phase. When universities, we have a lot of universities that participate in this conference. What would you recommend for universities and the research they're doing to help start the reliability mindset all the way back at the university level? Is there anything that we feel they can do?
I think the most important thing, I want to go back to what I just told Claude. It is total cost of ownership. Don't look at the work in the universities. They're in the invention world, right? They're inventing. They are developing new materials and new ways of doing things, or parts of materials. And part of it is it's happened in that world too. We all start with, hey, how do we reduce size, reduce cost, reduce? We start with the word of reduce as opposed to start with the word reliable. Do it as if your life depended on it. Start there. Don't do it as the one that gives the maintenance people exactly what the purchasing people want them to have, total cheapest cost. Look at longest life. Start with life and then work backwards. Okay, how do you reduce the cost if you give it the most important life? I think the next one is going to be expect the unexpected. So this one thing, what does the electrification of transportation do to the grid, to the world? Think about it. Henry Ford changed the world when he did this, the way he assembled cars, right? But Henry Ford, and he wrote in a book that I read years and years ago, I can't even remember where I read it, I'm looking for it, but supposedly Henry Ford looked down from his office, his scaffolding, to where they bench-built cars, and he had this idea, what if I could build a car that the people building cars could own? Because none of the people building his cars could own a Ford. They were too expensive. They were for the elite. That's where the assembly line came in. And so he created the assembly line. But if Henry Ford pushed out 1 million cars a month, or whatever he produced, but he didn't have gasoline to run them, what would happen? So a gentleman named Rockefeller in the Cleveland area, actually, there is the first refinery ever built by Standard Oil. If we didn't have gas stations built throughout America, we would not have been able to fill those cars up. He completely changed the infrastructure. We are going to completely change the infrastructure And the insulation that we use for charging stations, for cabling, for transformers, for step up, step down, for inverters, for everything ought to be a big deal. That's where they ought to start. What we do matters to the overall grid. I get passionate about it because my grandchildren are going to be, my sons are going to be driving around and they're not going to know what a gas-powered vehicle was.
Well said, Alan. I agree with you. Well said.
Thanks,
yes,
Nancy.
thank you. Great. Yes, very good. Very good. Is there any other questions? I want to thank Alan for a great presentation. It was a very good presentation. So everyone,
Thanks
clap
so
for
much,
Alan.
Alan.
Thank
Great
you.
job.
Yes, it's a great job.
Oh, I see those hands. Oh, there were hands raised. Is that a hand raise? Or... Oh,
No, those are
are
clapping.
clapping.
We're clapping for you.
Clapping, yeah.
You can't hear it. Well done.
Thank you all.
Yes,
All right.
very. Want to thank everyone. I especially want to thank Alan for his great presentation. That was very good. We really appreciate him coming to speak to us this year. A very good presentation. I also want to thank all of our participants for attending this year's conference. You guys are amazing bunch of people. We really appreciate your participation in this conference. And again, thank you to all of our sponsors. You guys help make this conference what it is. We really appreciate everything you guys do there, especially our platinum sponsor, Von Roll. We really thank you for your sponsorship there. Thank you.